While nucleophilic aromatic substitution was an addition-elimination reaction in which we had a nucleophile add to the molecule, some resonance happens, and then we eliminate, forming our benzene again and kicking out a leaving group. However, there's another mechanism which was found, which is called elimination addition, which does not require the presence of a strong EWG. You can just do it with a leaving group as it is. If you treat this with sodium hydroxide at an incredibly high temperature, you can get this reaction to happen. Of course, because we're going to make a phenol, we're going to need to protonate at the end. If we do that, we end up with the following. We can get it to happen by cooking it like crazy. Very, very high temperature, right? Obviously, this is a reaction that doesn't want to happen, meaning we have some high energy intermediates at play here. And interestingly, and probably more commonly, this reaction is done with sodium amide and ammonia, also at high temperature. And this reaction will do the same thing, except we'll end up with an NH2 on our benzene. But interestingly enough, if we have anything else on this ring, say a methyl group, and I'm going to use a bromine this time because I feel like it. If we do the same thing, same reaction conditions, we get two products with equal probability. We get the one that we expect, but we also get one we maybe don't expect. So we end up with one that's para, like our original molecule was, but we also get this meta product. And weirdly enough, they're in a 50-50 ratio. So it's not like there's one preference for one over the other. It's bizarre. So research was done into this. I think this was like in the 20s or something, so a long time ago. Experiments were done to figure out what's happening here. And the experimental evidence, which actually used a Diels-Alder reaction to prove the presence of this bizarre intermediate we're going to see, suggests a pathway of elimination followed by addition. And if we take a look at that last one here, the brominated one with the methyl group, and in fact, just because of the way that I've drawn this, I'm going to redraw my double bonds. Remember that with benzene, they're interchangeable. It can be either way. But since I'm going to be drawing on this side, I want my hydrogen there, or my double bond there. So the mechanism here for elimination addition follows, guess what? Elimination first. I guess we have NH2. Strong, strong base. We're going to eliminate our leaving group, leading to something very strange. Normally when we eliminate, right, we form a double bond, but we saw that with, vicinal dibromides, we could deprotonate both of them with strong bases, forming an alkyne, right? And the weird thing is this can happen within a benzene ring. And we end up with something very strange indeed. We have a triple bond there. Now, we have our methyl group down there. And I'll draw that out just so we are clear because there's all these lines. This is a triple bond. So this intermediate is called a benzyne. So benzene, all double bonds, alkenes, right? This is benzyne now. And the evidence for this is because we saw that, remember, we can do Diels-Alder reactions with alkynes, and they were able to trap this benzyne using a Diels-Alder reaction. So it's terribly unstable. As you can imagine, a sp hybridized carbon wants to be 180-degree bond angles, right? because that's the way the orbitals go. But this benzene thing has bond angles that are 120, right, for a hexagon, so not very stable. So that's our elimination step. And now the interesting part is we can now add to this. We can say, aha, I'm going to add to this benzene. And so in doing this, we're going to have our dear friend, well, it's probably actually going to be the ammonia because that's going to be more present in this. Because this thing is quite unstable, it's going to react with even moderate nucleophiles like ammonia, but there's just more of it, right? Here we go. Going to go ahead and attack. And interestingly, it could attack either side. That's why we're going to get this 50-50. We could attack, instead, the other side of the alkyne. And in doing so, we'll pop open our triple bond. And I'm going to, in fact, not show both of them. Just suffice it to say, it can happen on both sides. So when you attack that position, it's going to push the electrons to the next carbon. And in doing so, we end up with the following. So now we're back to our double bond. So that's why we're okay using a less good nucleophile here, because we're going to restore the aromaticity of our benzene. And so that should be, yeah, that's going to be a plus here. We'll take care of that in just a second. So with this, we're going to go ahead and have we can have either thing happening here. We can have our ammonia come around, get attacked, producing ammonia again. That'll take care of that negative charge. It'll just deprotonate an ammonia molecule. We regenerate our NH2 minus. We end up now with our protonated aniline ion, which can then be deprotonated by another amide ion or another ammonia, doesn't matter. But since this is basic conditions, we're going to go with the base attacking, and we're going to end up kicking off that proton, thereby giving us our weirdly meta-substituted one. And remember, the para one is just from it attacking the other position. The mechanism is exactly the same, it's just from the other side. So, sorry, NH2. If your ammonia attacks the top side, you just get the para-substituted product. The mechanism is the same, just switch the positions of the lone pair and the ammonia. And so, with this, we'll end up losing another NH3, which is great because that's our solvent anyway, not a problem. We end up with this plus the para-substituted one. So, bizarre mechanism. Cook the crap out of this, and you can get it to happen, but you do end up with a 50-50 mixture of products if you have anything else on your molecule. So, synthetically useful, maybe not, but still, it's important to know because we have options now. So you have all sorts of fun things you can work on with your synthesis. So we've talked all about EAS. That's been our predominant discussion. We've now talked a little bit about nucleophilic aromatic substitution and then finally elimination addition. And so this is really the last bit of our aromatic reactions. So I hope you've enjoyed it, and I hope you're having fun doing your synthesis practice problems.